Hello, everyone, and welcome to today's webinar. I'm Lisa Shaw, the Digital Specialist at SICK. SICK is one of the world's leading manufacturers of sensors and sensor solutions in industrial applications. Today, we are presenting the latest trends in LIDAR, presented by Aaron Rothmeyer. Just a little housekeeping before we get started. A recording of this webinar will be sent to you following today's presentation. Also, feel free to ask questions at any time during the webinar by typing your questions into the Q&A section on the right hand of your screen. We will take some time at the end of the presentation to address as many questions as time allows. Now, without further ado, we will turn our time over to our presenter, Aaron. Aaron is the National Product Manager for ranging products at SICK. He has been with SICK for almost 7 years, bringing over 15 years of experience in his role. In his role, he is the expert in laser ranging products, analyzing market trends, and finding growing opportunities where LIDAR would be beneficial. He also helped SICK launch the TIM 10K Challenge, supporting innovation with LIDAR technology in colleges and universities nationwide. Aaron, please take it away.
With pleasure. Thank you, Lisa. So again, my name is Aaron Rothmeyer, and I'm hoping just to spend about an hour with you today talking about LIDAR, where it currently is, maybe a little bit about where it's heading, just based on my experience with LIDAR over the last 15 years. Hoping to just share some of that information with you. So as indicated in the invitation, we've got a few topics to talk about today. Mostly, I want to cover a brief history of what LIDAR has been and what it's becoming. I want to talk a little bit about where LIDAR is becoming more sensorized, which is pretty much a term that we've coined to indicate that LIDAR is no longer this large, complex technology. It's becoming much smaller, much more efficient, and much less expensive. We'll talk a little bit about multi-layer or 3D LIDAR, which SICK does offer, and I'll showcase one of the highlight products that we've got in the multi-layer family. And then a key topic is always solid-state LIDAR, so I'll talk a little bit about what SICK has in that category as well. And again, like Lisa said, if there are any questions along the way, please do load them into the Q&A section. We'll try to review those at the end of the talk if we have time. So starting out, I want to begin by saying that LIDAR has been extremely popular in one particular market segment in the U.S., and that's what we call AMRs, or autonomous mobile robots, sometimes called AGVs, sometimes called AGCs, sometimes just called robots. The most recent term is AMR, so I'll stick to that. You can see a few examples here. We've got Fetch in the lower right-hand corner, AMR on Adept, mobile robots in the middle there, Mir, and Six River on the left. All fantastic examples of using LIDAR, mostly for navigation and anti-collision. So that's kind of what a lot of people think of when they think of LIDAR. If we ignore self-driving cars for a little bit in that whole discussion, a lot of the industrial applications for LIDAR do revolve around this type of device, which, again, mostly what they're doing with LIDAR and these devices is navigation and anti-collision. So they're really using the measurement data portion of LIDAR technology for the most part to do some really complex things with these devices. And so that's a really heavy use for LIDAR. But I want to mainly spend this hour focusing on some of the other applications that are a little less common, a little less understood, but just as powerful and just as capable at increasing a plant's efficiency and ROI. So to do that, I think we should start out by basically answering the question of where did it come from? And LIDAR has been around actually for an extremely long time. One of the first examples, I think the first patent for it came about in the mid-1900s for a device that was basically being used to map trees and map full landscapes, which obviously is still a pretty powerful use of LIDAR. But the first use of it in industrial applications came from our founder, Dr. Irwin Sick, who saw an opportunity to use light and to use light-based ranging, or LIDAR, to do safe applications, to make sure that a machine being used on a plant floor could be considered safe and not harm its operators. And that was kind of the goal of Dr. Irwin Sick, from the very beginning, was finding ways to use technology to make people's jobs safer and make, basically the world a better place. And so that's kind of how the first LIDAR came about from a safety standpoint. But it wasn't too much longer after that the market said, hey, this is great, this is a really cool product, but we don't really need all that safety functionality. Can you do something else that doesn't have all the stipulations and the requirements of a safety device? And so shortly thereafter, there came a device. This is a picture of the LMS 200, which was very popular as a non-safety laser scanner, or LIDAR, and it found itself in a lot of really interesting applications. Going way back to the early 2000s or so, and late 1990s, the LMSs were found doing applications such as like self-driving cars from a research standpoint. So some of you may have heard of like the DARPA Urban Challenge put on by DARPA in the early 2000s. A lot of those cars that were basically tasked with driving themselves through an urban environment were using the LMS 200s to navigate and make sure that they weren't running into anything as they drove themselves. So applications like that, and applications like open road tolling, where these same scanners are being used to scan vehicles as they travel along a highway to ensure the correct tolls are being implemented. Those are some of the really, really early applications of industrialized LIDAR. But what is LIDAR? Just from a very basic level, LIDAR operates on what we call the time-of-flight concept, which is a very well-tested, a very well-understood concept, which basically relies on the fact that we know the speed of light, through our atmosphere. And so what we can do is send a pulse of light, bounce it off of a target, and measure the amount of time it takes to get back to us. Obviously, that's a very short amount of time, but we've been doing this for quite a while. We've got very, very accurate clocks internally that can tell us very precisely how long it took for the pulse of light to get out and back. And so the time-of-flight concept you'll find in a lot of different devices. Ultrasonic sensors use time-of-flight. Of course, it's not light-based. We do have laser-based distance sensors that use a single pulse of light just to measure the distance to a single point or a single target. And then, of course, in LIDAR, we're also using the time-of-flight concept. What we do in LIDAR that's a little bit different than a single point distance sensor is we take that pulse of light, we bounce it off of a rotating mirror. So as you can see on the left here, we've got a 45-degree angle rotating mirror, and as the mirror rotates about its axis, the light pulse that's being bounced off of it is basically just swept horizontally or on a flat plane around the laser scanner. And so what that looks like, you'll see on the right, is essentially the mirror rotates. We fire the laser, as it rotates, and so we get all of these measurements essentially in a fan around the laser scanner. So as we do that over and over and over and over again, many, many times a second, we get a flat plane of measurement. And that's really the core technology that makes up all of our laser scanners. And it's really, really powerful, and it's really, really robust. There's not a lot of ways to fool this type of sensor, because all we're really doing is bouncing light off of an object. And so it's almost a physical, almost a tactile measurement. There's actually a pulse of light touching the object and bouncing back. We're not waiting for light to, come from the sun and bounce off the target and come to us like maybe a vision camera would. It's our own light. So it's a very, very easy and very robust technology to work with. But in the past, there's been a lot of difficulty in actually working with each one of these measurements because we would start out from a LiDAR standpoint just feeding data to some type of controller, which then the controller has to parse all of that data, has to make decisions off of that data, and it was really a fairly complex project, which is why some of the early adopters were, like DARPA, who obviously has quite a bit of tools at their disposal to filter and work with all that data, or some of the open road tolling companies that are able to work with all of that data coming into their controllers. It was a relatively complex concept, which is why over the years we've been able to add more tools and more functionality into our LiDAR devices to make them a lot easier to work with. So over the years, over the decades that we've been doing this, we've gotten to a point now where we're launching what we're calling Sensorized LIDAR. And the best way to describe that is really the TIM-100 and the TIM-150, which is the most recent, or which are the most recent products to come out of the TIM family. The TIM family itself has actually been around for, I'd say, about 7 years now as well. And the TIM family has always been our small end LiDAR, which is basically the smallest that we offer from a physical standpoint. It's also considered what we'd say the entry level of our LiDAR products. But there's still a lot of complexity there. So we've really, over the last couple of years, really narrowed that down to just what is the core offering that we need to consider this a sensorized LiDAR. And that is the TIM-100 and the TIM-150. So if we look at this slide here, it's basically showing the TIM-100 is a compact, very lightweight laser scanner. Weighs in at about 90 grams. It's still very robust, but we were able to strip out a lot of the weight to get down to just a very bare bones sensor. And with that, you get a range of about 3 meters or 10 meters for the 150, which is just slightly longer. So we'll delve into a little bit about what all these terms mean as far as HDDM plus and IO link and SOPIS and all that, but I really wanted to highlight basically the key applications at the bottom. There are certainly some AGV applications, but we also note that as far as bin fill measurement or height detection, the TIM stands out as a very easy way to accomplish that application. You can see here in the second picture from the left, we've mounted a TIM under a conveyor looking out over this bin. This bin, we want to know if it's full or empty. Previously, we could attempt to do this with, say, maybe like a light grid or something like that, but light grids can kind of get in the way of your process. You come in with a forklift and pick up the bin. You got to get the light grid out of the way in order to do that. So it's never really been a great way to check the level of that bin until now, honestly. With the TIM, we can go and we can mount, under the conveyor where it's safe from being damaged, and we can look out over the top of the bin and define just that area. And that's a really important point, is that even though we've got a 3-meter range or a 10-meter range in the TIM-150, with our SOPIS software, which is our freely downloadable SICK programming environment, the SOPIS software can allow us to basically modify the sensor and say, we don't want to look at the entire range, we just want to look at one particular area of interest. And we call that a field, sometimes we call it a zone. But this green area here indicates that we've created a zone that matches the size of the top of the bin, so that when an object breaks that plane, we can say, okay, an object fell through or an object is blocking the plane, so that now we know that the bin is full. We'll talk a little bit more about that on some upcoming slides. But a few key points here. Essentially, I could talk about the IP65 housing. IP65 to us is considered indoor ready. you know, you probably could use it outdoors, but we've got other devices that are IP67. So for the point of, for the TIM, we would say IP65 is best used indoors. In the TIM 100, you do get one field. So like we talked about on the last slide, the zone that you can create with the TIM 100, we limit that to just one field for the TIM 100. And quite honestly, that's enough to solve many, many industrial applications. For those that need more fields, we do have the TIM 150 available. The TIM 150 supports up to 2 fields. And the 2 fields, you know, perhaps you can set up like a left and a right, or a low and a high type of situation where, you know, you can set up different areas of the field of view and have a different output tied to each one of those fields. So there's some flexibility there in the TIM 150. And for your information, we do have other devices certainly in the TIM family that have more capability or more flexibility if that's necessary. We're picking a very small segment of the SICK LIDAR portfolio to talk about today. So we've got a lot of other varieties out there that can do a lot of different things. So one of the other things to talk about here is HDDM, which is basically how we improve our ambient light immunity. And it's also how we reduce cost and complexity of our components. And so HDDM, I just want to cover it real quickly because it's so key in the TIM family, and in particular in the TIM 100 and 150. You can see the power consumption over here is 2.5 watts. So 2.5 watts is an extremely small amount of power, especially when you consider previous LiDAR devices and even a lot of our current LiDAR devices that are consuming, you know, 22 watts or above just for standard operation. So 2.5 watts is really key, especially if you're using a mobile device, or, you know, maybe you've got something mounted on a cart with a battery. That battery is going to last a whole lot longer with a TIM than it is with, you know, one of our more power-hungry devices. And a lot of what allows us to do that 2.5 watt consumption is tied directly to our HDDM technology. And so I'll show you real quick here what I mean by HDDM. The HDDM is basically our way of, it's our own patented technology, and it stands for high definition distance measurement. And so previously, if we looked at a non-HDDM device, we'd have a single shot per measurement. So we oftentimes in LiDAR talk about angular resolution, and angular resolution is effectively how frequently we're delivering out a measurement or how frequently we're taking a measurement. And a non-HDDM device will basically fire out a single shot per measurement. And that's basically illustrated here, where we've got these blue squares indicating our measurements that we're making, and the red lines indicate our laser pulses traveling out and bouncing off of those targets. So that's the way LiDAR operated for a very long time. It's still certainly a very good way to do LiDAR. A lot of our higher end products still use non-HDDM technology. The issue with it is that the components required to do this are very expensive. So we're using very high power lasers, still eye safe, but a very high voltage laser to give one big impulse to bounce off that target and come back. And so there's a lot of cost and weight and inefficiency that goes along with using such a high voltage laser. That led us to develop what we call HDDM, which basically, if we look at this, allows us to use a much lower power laser, but we fire it much more often. So the analogy I usually give is that we've taken the non-HDDM devices, which use, you know, 50,000 volt laser, and fire it much like a cannon shot, you know, a big high power projectile. And now we've gone to a much lighter, almost like a laser that you'd find in like a DVD player, a very low power laser, and just send out a whole bunch of pulses. And by sending out a whole bunch of pulses, we can spread out the amount of energy that's required to get a reflection back. And as we spread that out, we're allowed to use much lower cost components, a smaller power supply, like I said, a lower power laser diode. And we're able to do a lot of cool things as well, like filter out ambient light. So HDDM, because now we're using so many pulses, we have a much better ambient light immunity, because now the odds of having our laser pulses affected by ambient light, say like a bright sunny day, are much lower. And so we've got a much higher ambient light immunity, which is a nice side effect of HDDM technology. So I hope that makes sense. I'm certainly able to answer any questions on HDDM at the end of the show if you still have them. But the long and short of it is, what does this type of technology do in a factory environment, in say a packaging environment? We found some really quick and really easy applications that are very popular in packaging and in end-of-line situations. So one of the biggest ones right now is a bin full application, where you can see in the top picture, we've got a TIM mounted right up here, and the TIM is basically just looking over in a horizontal plane as these bins travel underneath it. As we know, the TIM, if we set up a field or a zone to look for objects to be there, as the bins travel underneath, we're going to be able to get a digital output if that bin is too full. So this is a quick, easy way to verify, maybe as these bins are traveling into the next stage of their process, that the bins aren't going to cause some kind of disruption in the line by having product hanging out of them. So, it's a very quick, very easy way to use this sensorized LIDAR, or this TIM, to improve the uptime of a packaging facility. The other quick way that we've identified to use these sensorized LIDARs in a packaging environment is basically to set them up much like a pick-to-light system for bin picking. So in this situation here, we've got an operator reaching into a bin or pulling a bin out of a storage rack. The TIM can be positioned basically over the front of the bin just to look for the operator's hand. The picture here actually shows the light curtains that have been done, but this can all be done just basically with a single TIM. And as an example, I've taken some pictures, or I've used some pictures of our own operating environment, actually. This is a TIM that we've got mounted up in Germany, where we're producing all of our TIMs. And it's kind of ironic that we're using a TIM to monitor the production of TIMs, but we're looking down at the face of this worker's stand, and basically as they reach into these bins, we can monitor which bin they've reached into using the TIM. Got some pictures here showing this operator is reaching into the wrong bin. The wrong bin, he's looking up here and he sees that the screen has shown that, red indicates that he's reached into the wrong bin. Should probably try again. And so when he does reach into the right bin, you can see the screen turns red to indicate he's reached into the right bin. This is a quick, easy way that we've basically been able to improve our process and improve the reliability of our kitting stations to make sure that our operators, as they're following the bill of materials, as they're following the process to either kit or build a product, are simply grabbing the right components. And there's obviously a level of complexity here in a real world environment, because as the bins change from different sizes or different positions, or if the operator perhaps wants to use two hands to reach into the bins, that's obviously a level of complexity, but we have been able to adapt our systems in our German production facilities to account for those kind of complexities. Sometimes we have to add another TIM to look at a different side, or sometimes we just have to adapt our software, but it's very repeatable and it's very reliable in our process. And I think it would be in a lot of operating environments as well. So those are some of the really quick key ways that we're using LIDAR, not only what we've seen at our customers, but also what we're using in our own environments to improve our processes. From the entry-level TIM and TIM 100 that we were just talking about, I'd like to step into multi-layer, which is, some people call 3D. Within SICK, we refer to it as multi-layer on purpose, because as you'll see, while it has three-dimensional characteristics, multi-layer is just kind of a different animal. So we'll try to explain what that looks like. This is a nice graphic. I like this one because what it shows is that in the MRS 1000, what we have is not just a single plane that can, obviously be used for a lot of things as the TIM is shown, but we also have 3 additional planes on top of that, which basically just provide an extra layer of protection for your application. So the horizontal plane shown here is still capable of doing all the things that we just talked about, but then we've got 3 additional ones which can be used for if you're trying to detect an object at a long distance. The additional planes can help to provide an extra layer of detection so that if your object isn't correctly aligned with the 0-degree plane, for example, perhaps the 2.5-degree plane here will pick it up, or perhaps the 5-degree plane. It just allows a little bit more flexibility to your application so that if things aren't perfectly aligned or if things aren't 100% always going to be in the exact same position, you can use a multi-layer sensor to basically adapt for that situation. There's other reasons to use it as well. One quick example I can think of is actually down here, and I'll show you the situation here is pallet overhang, where the MRS 1000 is being used to scan a pallet traveling underneath the MRS 1000. As it does that, we're basically looking for any object that isn't supposed to be there. So a pallet traveling into a stretch wrapper, you want it to be relatively complete. You don't want objects sticking out, that might get caught up on equipment or might puncture the stretch wrap or anything else that might mess up your line. So the MRS 1000 can be used basically to look down at the pallet and determine if anything is hanging out or not. So the MRS 1000, because it's multi-layer, can account for pallets that aren't completely vertical. So if you look at this picture here, if we think of the red plane as being the 0-degree plane, it's going to look down at the pallet. As the pallet travels underneath it, it's going to catch anything that's sticking out. But if the pallet is tilted in any way, we could potentially have what we would call occlusions or shadows, where the 0-degree plane might not see it because while the pallet should be completely vertical, it's not. And so the 0-degree plane that the MRS 1000 sends out can actually be shadowed by the top of the pallet, so you can't see what's underneath it. What the MRS 1000 does a little bit different is because of those multiple layers, the other layers then could have a chance at seeing objects that the 0-degree plane can't see, which could be the difference between catching something that's sticking out of the pallet and not catching something that's sticking out of the pallet. So it's just basically an extra layer of redundancy that allows a process to be a little bit more robust. So going back to this slide, there's other good things about the MRS 1000 besides just the fact that it's multi-layer. It does have a fantastic opening angle of 275 degrees, which basically means that if you look in the upper right-hand corner, 275 degrees in front of the scanner is being monitored at all times. And so there is a little pie slice at the back of about 85 degrees that isn't seen, but we find in most industrial applications, nobody's needing 360 degrees for most industrial applications. So 275 degrees opening angle, and it also supports what we just talked about, HDDM. And there's another technology within the MRS 1000 called triple echo evaluation, sometimes called multi-echo. And so I'll talk a bit about what that means, because it is really important for what I would call like a non-ideal environment. I'll get to that just very quickly right after this slide. So the MRS 1000, we've got an IP65 variant, which, as I said earlier, is best for indoor use. We also have an IP67 variant. The IP67 variant, as most of you probably know, is great for outdoor use. Can handle all kinds of weather being thrown at it, not just splashes, but actually full immersion. It's a great product for outdoor use. And it also supports a wide temperature range, so -30 up to 50 Celsius, which is a pretty substantial temperature range. There's not a whole lot of environments in industrial situations that go below -30 or above +50. So great product for a variety of things. It does have a very long range as well. So it says down here 16 meters at 10%. I want to be clear that that's what we call worst case scenario. So this 10% is effectively what we would see on a very dark target. 10% refers to the reflectivity of the target that we're shooting at. So 16 meters is what we see for, say, a black object or maybe a car tire. We would still be able to detect that object out at about 16 meters. The best case situation that is much more common is up towards 90% reflectivity or somewhere near max, which is our best case scenario. And you'll see that the ranges there are closer to 30 meters and 64 meters. So just to give you some idea, a lot of the targets that you'd be shooting at, say cardboard boxes or pallets or something along those lines, are probably going to be close to the 90% range, so somewhere in the 25-meter ballpark or so. So that's a very long range that comes out of the MRS 1000. And a lot of that is due to the HDDM technology and then the multi-echo technology, which I'll talk about real quickly here. So we've talked a lot about what LIDAR is based off of today, that time of flight technology. And we've talked about HDDM and we've talked about non-HDDM. And so if we look at just a single laser pulse and we forget about all that other stuff, we look at just a single laser pulse, we have to remember that in an ideal case, that laser pulse is probably going to travel out to the target and bounce straight back with nothing in the way, which is basically how time of flight technology works. But in the real world, a lot of things can happen between you sending out that laser pulse and it bouncing back. Even in an indoor environment, there are a lot of things that can get in the way and cause basically small reflections. So here's a nice diagram that we designed that shows basically some dust flying through and some fog and the way that we react to that. So what it's trying to show here is that this pulse of light that's traveling out is hitting the dust first. It's saying it's at about 3.57 meters. And as it hits that dust, not all of the light is reflected back, but some of it is. And so we call that an echo. And so as we catch that echo, if we did not have multi-echo evaluation, the scanner would basically see that echo and say, okay, I saw a target. Here's your distance, or here's your decision. Maybe it interprets it as the bin being full or a pallet being there when the pallet isn't actually there. It basically reacts to that as an actual object, which isn't really ideal. And perhaps there's fog or some mist in the building. I've been in a lot of die casting facilities that have a lot of just fog from the process in there. And so that fog as well can create an extra echo coming back. And then inevitably, as the beam works its way through all of this mist and dust, it actually ends up hitting its target. And so then it bounces back off of the target as well. And if we did not have multi-echo functionality, again, we basically just see the first echo that comes back and respond to that, which is definitely not ideal. That's basically what we would call noise in the system. So in most of our mid-range products, we incorporate what we call multi-echo evaluation, which basically means we're going to catch that first echo, but we're not going to respond to it. We're going to wait. And so we wait, and if we get a second echo back, great. Again, we record it, we acknowledge it, but we don't respond to it. And then we wait until, in this device, we get up to 3 echoes. And once we get that third echo, we say, okay, which one do we actually want to take action on? And most of the time, we just set it to last echo. So whatever the echo is that comes in that's the latest, I guess, the farthest away, we react to that. And in nearly every case, that means that if there's nothing here and it's an ideal case and it's just, we're working in a vacuum or whatever, the light bounces off the target, comes back. That's the last echo. If something gets in the way, like fog or dust, those echoes that come in before the last echo, so we ignore them. And we can set it to react to first echo if, say, we want to detect dust or something like that. We can do that. But in most cases, we set it to last echo so that it just sees the target and ignores everything else. And so I'll say, just from my experience, this technology is critical for the success of LIDAR in any kind of non-ideal environment. Using it outdoors is absolutely necessary because so many things can happen outdoors with rain and snow and fog and that sort of thing. Using it indoors is still a very nice function to have because I know not all production environments are, like clean rooms. There's certainly a lot of things that happen in production environments that most people would consider non-ideal. And that's really where the multi-echo evaluation shines, is in those non-ideal environments. Otherwise, outside of that, the MRS 1000 is a great product. I'll cover real quickly, again, the application here, which is basically just looking for overhang on pallets. We can also do volumetric calculations as the pallets travel underneath. We can determine the size of those objects that are traveling through the pallet or down the conveyor. So a lot of things can be done with multi-layer technology. A lot of things can be done with LIDAR in general. But one of the key ones here is basically scanning these pallets. The last topic I wanted to cover is probably one of the most exciting, and that's what we call solid-state LIDAR. Now within SICK, we've been chasing the solid-state LIDAR goal for a long time. We've been developing products for quite a while that fit into the solid-state LIDAR category. And one of those is called the Visionary T. And it's shown here in 2 different forms. And basically what solid-state LIDAR does differently than our other LIDAR devices is that there's no moving parts, hence the term solid-state. There's no rotating mirror. There's no motor spinning that with an encoder wheel on it or anything like that. There's no moving parts, which can be beneficial to certain applications. I mean, our devices that do have rotating mirrors, they're still fantastic devices. We've got mean times to failure of upwards of 20 years for a lot of our devices, even if they do have a motor involved. But we're still also working on solid state because obviously it's got its own benefits as well. So Visionary T is what we currently have for solid state LIDAR. It's got some really great applications that you can solve that haven't been able to be solved with any other devices. So the Visionary T, what it does a little bit differently is instead of having a single plane or even multiple planes, it has basically a camera view of everything that it looks at. So if you picture like a snapshot camera taking a picture of a scene, every pixel that's associated with that image that you've taken now also has a depth associated with it or a distance associated with it. So you can see up here in the upper right-hand corner, we've got a Visionary T looking down at the same bin that we were talking about earlier. Only now, as we look down in that bin, we're getting a true 3D image of whatever is in the bin. So it's not some kind of pass-fail situation. We can actually identify, for example, if we've got objects laying on top of other objects, we can use the visionary T to identify which object is on top so that a picker or a robot can come in and grab the next object. And the issue up until now with the solid state technology is that there's always been a lot of complexity in parsing that data. So, if you think about taking a camera image and associating a distance with each pixel, and then also a confidence value with each one of those pixels, that's a lot of data streaming out of the camera. And some controller has to actually parse all that data and do something interesting with it, which that was a pretty high bar of entry to actually working with this device. So what we've done is we've released the most recent version actually has built-in configuration software so that in SOPIS, you can come in and basically do something very similar to what we've been talking about with the other products, which is define a field or define a zone and look for objects within that zone. So what that's allowed us to do is applications like this, where, and I apologize, this is a great video, but we wanted to just go with pictures for the purposes of the WebEx, but we can make this video available afterwards for you to access. But what this is showing is that basically we've got 5 bins here. We've got 3 light-colored ones and then 2 smaller dark-colored ones. And right now, they're all empty. And so on the right, you can see essentially what the visionary sees, which is a point cloud. And that point cloud, each one of those greenish pixels there is basically showing a distance. So you can see the edges of each one of the bins. Some of the edges are breaking the planes that we've set up, which change the planes from blue to purple. That purple is indicating that, yes, something is there. But what we're really interested in is what is in the bins. And so if I click to the next slide here, you can see here we've placed an object in the lower left-hand bin, and that object is now breaking that plane. So you can see now if I go back up, the bin in the lower left-hand corner changes from blue to purple to indicate that now there's an object there that wasn't there before. And so now we can check and make sure that those bins are empty, say, before they go off to some process. Or we can count the objects that are in there, if we incorporate some more complex algorithms. But just from a very basic standpoint, being able to tell whether or not an object is there using the solid-state LIDAR technology is really easy and really reliable as well, because we are still functioning based off of that same time-of-flight principle. So it's a pretty solid technology, and it's becoming much, much easier to use. So that allows us to use it in some more applications, because now we don't have to have a separate controller there parsing and trying to interpret all of the data. So on the left here, we've got applications that show basically, is the bin full or is it not? Now, like I said earlier, we don't have to have a TIM mounted at the top to tell whether or not it's full. We can really actually look down into the container and see what's in there. There's even the possibility of counting what's in there and doing that with the visionary T. It can also be used in, say, security applications in the middle there. So in this application, we want to allow people to get close to the art. We want to make sure, they're within range, but we really would rather they not touch the art. So here we've created basically a green cube that if anything enters that cube, the size of the art itself, we get an output and we say something is there, we sound an alarm, we call over a guard, something like that. And it doesn't have to be art, and it doesn't have to be security. The same thing can be used for, say, making sure somebody's not standing in a insecure environment or in a non-safe environment. We want to make sure that this isn't being used to protect, human lives because it is not safety rated, but just, access control, making sure that nobody's in, a storeroom when they're not supposed to be in that particular storeroom. That's a great application for the visionary T. Or making sure that pallets, have been cleared away from an area before an AGV comes and drops in new pallets. Another great application for the Visionary T. Overall, its specifications are pretty wide, I would say. There's a lot of things you can do with the Visionary T. Basically, anything out to about 8 meters is really easy to do. So that gives you about 24 feet or 25 feet, out to which you can get basically a picture back of whatever you're looking at with distances associated with it. The detection angle down here is 70 degrees or so by 55 degrees. So if you picture what that looks like, that's basically a volume, or a pyramid of area that you can use to monitor your process. So for example, this application here in the middle is showing 2 Visionary Ts looking down and basically forming a box around this car, basically verifying whether or not the doors are open or whether or not the trunk is open just by looking, down from the top. And it is a quick snapshot as well. This technology LIDAR technology can be used for these types of applications. But a lot of times, if you want a true volume, you have to have some kind of movement required. So you either need to move the LIDAR or you need to have the target move underneath the LIDAR, one or the other. But in this situation with the Visionary T, you're taking a true snapshot of an entire volume. So because of that, you can basically do whatever qualification or whatever measurement you need to do without ever having to have the target move underneath the sensor. And it is still IP67, and it is still robust enough to deal with light up to about 50,000 lux, which is right up there with our other LIDAR sensors. So it's a very robust technology. It can be used in a lot of interesting applications. The last application I wanted to talk about with the Visionary T is in packaging. And this is basically a great way to use a Visionary to basically figure out where the package is on this conveyor belt. So we've got a robot with a suction gripper coming in to pick up these cartons and stack them on a pallet. Essentially, we've got a Visionary mounted on the side of that gripper, looking down, so that if the cartons that are coming down the conveyor aren't positioned perfectly, the Visionary can identify them, figure out what their center of mass is or their centroid, and have the robot come in and pick that up properly and go drop it on a pallet. Without the Visionary T there has to be some kind of other means to account for misalignment in the system. Otherwise, perhaps the robot that's coming in can only contact it with a couple of suction grippers, not quite get good enough of a grip. All kinds of things can happen when that situation occurs. You can have dropped packages or crashes or downtime, all of which we'd like to try to avoid. So the Visionary T is just a quick, easy way to basically say, is the carton where I expect it to be, yes or no? And if it's not, it can actually feed some pretty complex data out to the controller to say, okay, here's how you need to adapt to this misaligned container. So it's a really cool technology. I'm really excited about where solid state is going, and I'm hoping to share, more details about where SICK solid state LIDAR is going in the near future here. But for now, the Visionary is really a very capable product that's able to do some really, really neat things in very flexible environments. So with that, I'd like to open the floor to any questions that you guys have. I'd be happy to answer anything you've got, or at least attempt to answer.
Awesome. Thank you, Aaron. Yeah, we'll go ahead and take some questions, as Aaron mentioned. As a reminder, you can type your questions into the Q&A section on the right-hand side of your screen. And Aaron, we have a few for you. One listener asked, I am looking at ADR, automatic device recovery. Do your devices have this?
Well, I did say I would try to answer all of your questions. Automatic device recovery, Mike, if you're able to elaborate on that, I'd love to try to answer that. I'm not entirely familiar with the automatic device recovery or ADR functionality, but if I don't get a response from you, I'll try to answer it with you directly.
Awesome. Another question is, what software does SICK offer to help process the point data that is generated by the SICK LIDAR scanners?
Sure. As I mentioned earlier, the LIDAR data that comes out is quite complex, and obviously there's a lot to do when trying to interpret all that data. And so right now, what we recommend is utilizing the built-in functionality of the TIM and of the MRS 1000, where basically we take all that data and we filter it down to basically a yes or no question. Is there a product there? Is there a target there? Or is there not? The point cloud data is an entirely different topic, which is certainly interesting to work with, but there's a lot of complexity there as well. So SICK right now doesn't offer any software that, say, would allow you to make decisions based off of that point cloud data. Or I've seen some customers want to try to take that point cloud data and turn it into, say, a SolidWorks file or a CAD file. That is usually somewhere that we need to bring in a third party to help work with that data. One of the best third parties that I am aware of would be the OSRF, or Open Source Robotics Foundation, who manages right now ROS, which is the robot operating system. That is an open source tool. It is not something that SICK creates or makes in any way. However, we do write our own drivers to operate with the ROS environment. And so that is, obviously it's not going to fit all applications. Nothing ever does. But ROS does have a lot of power. And so if you look into the robot operating system, that might be a good solution for you.
Great. And going back to our first question about ADR, automatic device recovery, Mike is asking, is there a setting that you can set up on the device so when it gets replaced, it gets reprogrammed with those previous settings?
Yeah, thank you very much for elaborating. So the ADR functionality is something that I usually associate with IO-Link, which IO-Link, most versions of IO-Link support this, I guess what we'll call ADR, which basically means that the device can be cloned very quickly, which only a few of our LiDAR devices support IO-Link. So the TIM 100 and TIM 150 that we showed at the beginning, those are IO-Link devices. I believe they still have one more revision to go before they will support such a function, but because they do support IO-Link, that functionality is pretty much ready to go. We just have to finish working with it. So otherwise, the other devices, what you would have to do is actually, when you program them, when you configure them in Scopus, you can store the device file that you've created on a laptop, on a thumb drive, on a local network. And then basically when you want to go replace that, you connect to it via Ethernet or sometimes USB and push the file down into the device. So it's not quite what I would call ADR, but it does still allow you to bring back a sensor back to its original state.
Great. This is a question from Peter. He says, in my industry, we detect if cardboard box flaps are up, and we have several box sizes we deal with on a single conveyor. We are currently using an analog light curtain and a barcode reader. How well does the MRS 1000 work for flap up detection?
Good question. Obviously, in your situation, you've got a lot of variability with several box sizes. There's a lot going on. I have to assume that the barcode reader, or I'd like to assume that the barcode reader is identifying what box type it is. If that's the case, it would be relatively simple, and I'll tell you why. If the barcode reader is able to tell you what the overall dimensions of the box should be if the flaps are properly in, then we can actually, in the MRS 1000, in some of the TIMs, in pretty much any of our LiDAR sensors, we can load basically multiple jobs. And those jobs can be selected via inputs or via Ethernet, so that, say, you've got box 3 traveling down the line. The barcode scanner says, okay, box 3 is here. It should only be, 200 millimeters tall. We can switch a job to box 3 in the MRS 1000 and say, okay, if anything greater than 200 millimeters comes through, we set up an output. And so, if the barcode reader is able to provide that level of detail, or the system, using the barcode reader can do that, the MRS 1000 could absolutely adapt to that relatively easily. I think what the MRS 1000 would have difficulties doing is doing it dynamically without any input, unless there's some kind of extenuating circumstances. I would say the MRS 1000, isn't smart enough at this time to say, for example, the conveyor surface is at 800 millimeters and this box is at 250, and that's not right. It would have to have some kind of input to say what it's expecting, if that makes sense. I hope it does.
What is the update rate of the Visionary?
For that, I'm going to flip back a couple screens, and I hope got it. I can tell you, here minimum response time is less than 160 milliseconds. And it's a bit variable because the more volume you're watching and the more tools you're utilizing within that volume, the more the response time is going to increase. So 160 milliseconds is currently considered max. But if you're using, very basic tools and looking at a very small area, so if you're focused in on a very small section of the field of view, that could be reduced substantially. I would say less than 100 milliseconds would be very easy to accomplish.
Cool. Does the solid state communicate via the popular field buses?
Not yet. Right now, we've got a few functions within the Visionary T that we're able to support. One is, like I talked about, digital outputs. So is an object there or is it not? We've got 4 digital outputs that we can utilize to switch, whatever PLC or whatever is going on in the plant. Otherwise, what we support is just raw Ethernet TCP/IP. And I did say TCP/IP, not Ethernet IP. And what that basically looks like is it's almost like Modbus, just a long string of measurements spit out in hexadecimal ASCII. That is not a popular field bus, but it is something that's currently, it's been used quite frequently, especially if we go back to ROS, so the robot operating system. Systems that are designed to parse that type of data do it quite readily, quite easily. But we do not yet support Profinet or Ethernet IP.
Awesome. We have time for one more question, and this question comes from Joe. And which LIDAR models have safety certification?
I'm glad you asked. Safety certification in LIDAR is a much larger topic. And I will say that our safety division within SICK have a wide variety of safety sensors that all meet basically PLD, whatever the highest level of safety certification currently needed. We've got the Microscan 3, we've got S3000, S300, many different devices that all meet very high level safety certifications. There is also a version of the TIM that we did not get to today that supports what is called PLB, or B as in boy, safety certification, which is basically, if you're not familiar with it, devices that are able to protect against applications that have a lower level of risk. So it's called the TIM 781S or 361S. They're both designed, they both have the same TIM body that I showed in the first few slides, but they're both designed to basically protect low risk applications where somebody's life isn't at risk. They're not going to have to go to the hospital if something goes wrong, but applications where there is certainly risk involved. For example, maybe you don't want somebody to get bruised. If you think about like a collaborative robot, collaborative robots are great. They're a fantastic technology, but you can't necessarily say that they're safe until you know what process they're doing, what's on that end effector. Perhaps it's an object that you would not want to get hit with, even if it's traveling at a fairly low rate of speed. And so products like the TIM 781S or 361S, with their PLB certification, can certainly be used for those types of applications, low-risk applications. But again, SICK has a wide variety of LIDAR devices that have, all variety of safety certifications. So it's a much larger question. We'd love to follow up with you on that at a later date.
Thank you so much, Aaron. That's all we have time for today. But as a follow-up, we will send a recording and Aaron's information if you have any more questions and want to email him directly. Please visit also sick.com to stay in the know on our upcoming webinars and trainings. Have a great day. Thanks again.
Thank you.